Alright, hey everyone. Let's go over probability and statistics that you need to know for Algebra 2 and the regents. So let's just get started. Now this packet is in Google Classroom and it's in the description. Also, it might not be what you got in the classroom, but just follow along. We'll go through all the problems together. All right. So in probability, we want to start with the probability of an event happening. All right, an event is just something happening. Let's take a look at an example like a six-sided dice, right? Boom. Sorry, I'm not an art teacher. All right, six-sided dice, and we say the probability of an event happening is the probability of a successful outcome over all the outcomes. Let's say I want to roll a 4, okay? So there's only one side of the dice that's 4, so that's 1. And the amount of outcomes, all the rolls that can happen is 6, right? It's a six-sided dice. So the probability is 1 over 6, or 0.167. And now, in probability, there's also something called a complement. So P of not 4. That's how you can think of the complement. So how do you do that? In probability, you either start at 0% or something that cannot happen at all, or 100%, that something will definitely happen. And so in probability, to find the complement, we take the chance of all outcomes, which is 100% happening, which is 1, and we subtract the probability of 4 happening, because we want not 4, we want everything else, and that's 1 over 6. 1 minus 1 over 6 is going to be 5 or 6, right? That makes sense. There's 5 sides in a dice. There's 6 sides in a dice. Only one of them is 4. And if I don't want 4, I can roll the other 5 sides. So that's what the basics of an event and a complement is. Let's do some examples. Factory recorded that over the past year, 6,000 good widgets and 2,000 faulty widgets. So maybe we could say like the probability of good is going to be 78,000 over some number n, which is all outcomes, and probability of faulty is going to be 2,000 over n, which is all outcomes. Now, what is the all outcomes? What we want to do is we want to add the good widgets and the faulty widgets, which is 78,000 plus 2,000, which is going to be 80,000. Right? And what is it asking? Or what is the probability that a widget will be faulty, which is this one, which is going to be something like, if you put in the calculator, 0.0025. All right, or if they ask for the percentage is 2.5%. Remember, they're asking for probability, so this answer, 0.0025, is good enough. Selena plays on the softball team. She has 8 hits in 20 times at bats. All right, so that's pretty good, I think. Based on past performance, what is the probability she will get a hit in her next time at bat? So this is basically asking, like, what's her batting average? Right? We could use that to guess percentage that she might hit a home run, right, a single, a triple, whatever, some sort of hit. So what we do is probability, right? Successful outcomes here is 8. 20 times at over 20 times at bat, it's going to be 0.4, which is very, very high. All right, now let's move on. Now in probability, we also have intersections and unions. We're down here now with the green arrows. All right, let's consider some situations like a deck of cards, right? We could have an event that a card is red and a king, right? So how many cards are red, right? And how many cards are kings? So we take the intersection of that. That's and. And is almost always going to be, not almost always, it will always be smaller than union. So let's find this card is red and a king. So the probability of a card being red and a king is going to be, let's see, how many red cards are there? Half the deck is red, right? And how many kings are there? 4. So 2 of those kings are red. So it's going to be 2 over 52, which is going to be 1 over 26. So that's pretty low, right? Now another event could be something like this, which is the union. The probability is card is red or a king. So the probability of red or a king, let's break this down, right? So what's the probability of it being red? Half the deck is red. So that's 26 out of 52. And the probability of things being kings, right, is going to be 4 out of 52. But we have to subtract their overlap, right? Because we're counting 2 kings twice, because there's 2 red kings and there's 4 kings in total. So we're going to subtract another 2 kings. So we're not counting these kings twice. And that's going to be 28 over 52. So as you can see, unions are almost always larger. Unions, we're kind of adding stuff. And intersection, we're kind of finding what they both share. And it's always going to be smaller. Let's do some examples with that and compound probability to see how things work out with the math. All right. Number 9, let's get started. Number 9 right here. 3 fair coins are tossed. What is the probability that 2 are heads and 1 is a tail, right? So we got to find the probability of rolling a head, and a tail. Now, since the coins are fair, the probability of rolling 1 head is 1/2. Rolling a second head is a half again. Rolling a third head is half again, which is going to be 1 over 8. And that's it for number 1. You get that on the regents? That's an easy question right there. At least I think so. Now let's take a look at something a little more complex, which is dealing with intersections. Number 10. The probability that it will snow on Sunday is 3 out of 5. So P of S equals 3 out of 5. The probability that it will snow on both Sunday and Monday is 3 out of 10. Remember the word and, so that means intersection. S intersection M is 3 out of 10. All right. So let's take that into consideration. All right. Now it's asking, what's the probability that it will snow on Monday if it snowed on Sunday? All right. So now it's asking us to find the unknown variable, which is it'll snow on Monday. We have the probability of snowing on Sunday and the probability of snowing on both Sunday and Monday. So this is basically just a formula. It's an independence formula. It's something that's given to you on the regents. What the formula here is P of the intersection S intersection M is going to be P of S times P of M. Now we kind of have most of that information here. Now we just have to kind of solve. So P of probability of snowing on both days is going to be 3 out of 10 equals, and the probability of snowing on Sunday is going to be 3 out of 5. And what we're missing is the probability of snowing on Monday. So we want to get this probability of Monday by itself. I'm going to multiply both sides by 5 over 3 to cancel this out. So I'm going to get 3 over 10 times 5 over 3, which is going to be 15 over 30, which is 1/2. So my answer is 3, 1/2. All right, let's do the next question. The probability that a student owns a dog is 1 out of 3, and the probability that a student owns a dog and a cat is 2 out of 5. Again, it's kind of the same exact example here. Let's break this down again. So P of D equals 1 out of 3. Probability of owning both dog and cat is 2 out of 15. Now, again, we're doing the same thing here. We're going to equal, say, 2 out of 15 equals the probability of owning the dog, which is 1 out of 3, right? times the probability of owning the cat, because that's what we're looking for. Again, I'm going to multiply this by the inverse, which is 3 on both sides. So that's going to be that's going to be 3 times 2 over 15, which is going to be 6 over 15. And that's my answer. I can reduce this to 2 out of 5. All right. Let's take a look at the next example. A student council has 7 officers, of which 5 are girls and 2 are boys. All right. So n equals 7. I'm going to write this down. N equals 7. And the 2 officers chosen at random to attend a meeting with the principal. Taking away class time. I don't know why. What is the probability that the first officer chosen is a girl and the second is a boy? All right. So there's a couple of things going on here, right? So what is the chance the first chosen is a girl? So what's the probability of the girl going, right? So what's the probability of the girl? Now, 5 are girls, so that's going to be 5 out of 7. All right. So we send her. We send one of the girls over. All right. How many people are remaining, right, after we send one of the girls? There's only 6 people remaining here. So, and the second one has to be a boy. So out of those 6 people, how many are boys? So 2 of them are boys. So again, we multiply here. 5 out of 7 times 2 out of 6, which is going to be 10 out of 42, which is this number right here. Again, taking away class time, principal should not be doing that, especially this close to the regents. All right. Bob and LaQuisha have volunteered to serve on the junior prom committee. The names of 20 volunteers, including Bob and LaQuisha, are put into a bowl. If 2 names are randomly drawn from the bowl without replacement, what is the probability that Bob's name will be drawn first and LaQuisha's name will be drawn second? Similar to the previous example. All right, there's n is 20. So n is going to be 20 here. And the 20 volunteers include Bob and LaQuisha. So they're in it. We're not adding and 2 extra volunteers. If 2 names are chosen at random without replacement, key, that means we choose a name from the pot or from the raffle and we don't put it back. What is the probability that Bob's name will be drawn first and LaQuisha's name will be drawn second? So the probability that Bob's name will be drawn first, there's 20 people, only 1 Bob. Is going to be 1 out of 20. And the probability of choosing LaQuisha's name after, there's 19 people left. LaQuisha's one of them. It's going to be 1 over 19. And that's going to be this option right here. All right. Let's do 14. Mr. Yi has 10 boys and 15 girls in his mathematics class. If he chooses 2 girls at random to work on the blackboard, what is the probability that both chosen are girls? All right. So, again, very similar examples. So there's how many people here? N equals 25, right? 10 boys, 15 girls. All right. So he chooses 1 girl, right? He chooses 1 girl. And how many girls are there in the class? So the first, choosing 1 girl, the first girl is going to be 5 out of 15 over 25. Now he chooses the second girl, right? So the 1 girl's gone. So we can't just replace people like that, right? People are unique. So how many girls are left? There's 14 girls left. All right. There's 14 girls left. And how many people are left out of the pool? Remember, we already took one of the girls out. It's going to be 24 people left in the class, students in the classroom. So this is going to break down into, like a number. Let me put this in the calculator. It's going to break down into 7 over 20. All right. So the chance of having a girl go up and then having another girl go up is going to be 7 out of 20. All right. Let's take a look at the next example, number 15. There are 4 students, all of different heights. who are randomly arranged in a line. What is the probability that the tallest student will be first in line and the shortest student will be last in line? Wow. Okay. Well, that sucks. All right. So, 4 students, all of different heights. So the first n equals 4. Oh my god, n equals 4. All right. What is the probability the tallest student will be first in line? So out of the 4 people, who's the tallest student? Right. One of them is the tallest. Doesn't matter how tall they are. It's gonna be 1/4. And then he goes. All right. And then how many students are left? There's 3 students left, and then we gotta choose the shortest one out of that. The shortest king out of that. That's gonna be 1 out of 3. There's only 3 kids left. Only one of them is gonna be the shortest, and that's gonna be 1/12. Let's take a look at the next example, number 16. There's 6 apples and 5 oranges in one pear. So 6 plus 5 plus 1 is gonna be, my n is gonna be 12. I'm gonna keep that in mind. His friend takes 3 pieces of fruit at random without replacing it. So he takes a fruit, he doesn't put it back. What's the probability that all 3 fruits taken are apples? So maybe pause the video, try it yourself, and then come back and see the answer. All right. So the probability of getting an apple, the first apple, is going to be, how many apples are there? 6 apples out of, let me use a different color here. It's going to be 6, let me erase this. I need more colors. All right. 6 apples out of 12 altogether. All right. And then I'm going to multiply. And then I'm going to get another apple. There's only 5 apples left. And there's only 11 fruits left. And then another apple is to be taken. There's 4 apples left. And there's only 10 fruits left. And this is going to give you a number. If you multiply this all out, this will give you 1 out of 11 after you reduce everything. And that's the answer. And the process is important, getting to the process. All right. Let's use blue. All right. Vince buys a box of candy that consists of 6 chocolate pieces. So I'm going to write n equals 6. 4 flavored pieces plus 4 plus 2. So n is going to equal 12. He selects 3 pieces of candy at random without replacement. Calculate the probability the first piece selected will be fruit flavored and the other 2 will be mint. All right, so let's do the first part. So he wants, he's going to draw the candies without replacement. The first piece will be fruit flavored. So how many are fruit flavored? 4, right? So 4/12, and then the next 2 will be mint. And then what's the probability of getting a mint? It's going to be 2. 2 pieces are left of mint, but there's only 11 candies left. And then getting another mint is going to be, there's only 1 piece of mint left, and there's only 10 candies, and that's going to give you a number, right? That's going to give you 8/1320, right? All right. And then calculate, and then let's take a look at the next one, which says calculate the probability that all 3 places selected will be the same type of candy. Oh boy, that is something else. All right. Okay. That is a big problem. All right. So I'm going to, for the sake of time, I'm going to skip that. If you want to know how to do it, ask me in class if you're actually watching the video. Because it's a very long problem. All right. I'm going to move on to number 18. Okay. A bottle, we're right here, 18 now. A bottle contains 12 red marbles and 8 blue marbles. A marble is chosen at random and not replaced. Then a second marble is chosen at random. Determine the probability that two marbles are not the same color. Determine the probability that at least one of the marbles is red. Okay, all right. So let's get our n here. Our n is going to be 12 plus 8, 12 plus 8, which is going to be 20. All right. And remember, we're doing this without replacement. All right, so marble is chosen at random and not replaced. And then the second marble is chosen at random. So determine the probability that two marbles are not the same color. So let's say first one I roll is red. And that's going to be 12 out of 20. And times, and then it's not, what's the probability of not rolling, or not picking, rather, another red marble? Well, all I have left are blue, so there's going to be 8. There's 8 blue left, and there's only 19 marbles left. So it's going to be something. All right, it's going to be 96 over 380. But we're not done, because we can think of this in the opposite direction as well. We can think of, hey, let's roll, right? Let's roll a red one first. Let's roll a red one, which is going to be 8 out of 20. All right? All right. And then we're going to draw a... Sorry, give me a second. 8 out of... We're going to draw a blue one first, right, in the second part, which is 8 out of 20. And then we're going to pick up a red marble. So there's 12 red marbles, and there's only 19 things left, right? As you can see, the denominators here are a little different. So it is going to give us a different value. So if we, again, do this, this is going to be 96 over 380, blah, 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 which is going to be, and then we have to add these up, because, again, the chance of drawing red first and then blue, and then we're also adding the chance of drawing blue and then red. So we're going to get 96 from here plus 96 from here over 380, which is going to be 192 over 380. And that'll be the probability, rolling one after another. All right. Now it's a little different. Now it's saying determine the probability that at least one of the marbles is red. So it's asking what's the probability of you getting all right, this one. Let me change colors. Determine the probability that at least one of these marbles is red. I'm going to do this down here. Right. So what's the probability of drawing red, right? It's going to be probability of red, P of R, is going to be 12 over 20, right? It's going to be 12 over 20. All right. And now wants to know that at least one of the marbles is red. So there's a lot of ways to do this problem. What we have to do here is what's the probability of just rolling anything at all, right? So the probability of rolling anything at all is 1, right? It's 100%. So, and then we have to make sure we don't roll 2 blues, right? Right? We want to make sure we're not rolling 2 blues, because we want at least 1 red here, right? So we have to do probability. We don't want this. We don't want to roll blue and then blue again. We don't want that. That's the probability we're like, hey, we don't want to roll 2 blue things at the same time. So we have 1 is 100%, 1 minus probability of rolling blue. The first blue is 8 out of 20. And rolling the second blue is 7 out of 19. And if you work this out, this is going to give you 380 over 380 minus 56 over 380, which is going to be 324 over 380. Remember, the probability of at least one of them being red is the same thing as saying the probability of not rolling 2 blues. All right, so the last example here, number 19, I'll leave as an exercise for you to do, and I'll leave the answer right here. The answer for the first part is, so maybe pause, is going to be 5 out of 8 times 3 out of 7, which is 15 over 56. All right, and then the second answer will be 20 out of 56. And the third answer will be 26 out of 56. Again, leave that for you to do, and so we can move on to the next couple of problems. All right, now let's take a look at 20. Fun example. Throughout history, many people have contributed to the development of mathematics. These mathematicians, including Pythagoras, Euclid, Hypatia, that's a woman out of this entire list. Euler, Einstein, Agnesi, Fibonacci, and Pascal. What is the probability of the mathematician's name selected at random will start with either the letter E or the letter A? So there's 8 mathematicians total. So they want to know how many is going to start with E or A. So this one starts with E. That's 1, 2, 3. This one starts with A. So that's 4. All right, so that's 4. That's 4 out of 8. All right, that wasn't that bad. All right. Now, so the next one's asking, the faces of a cube are numbered from 1 to 6. If the cube is tossed once, what is the probability that a prime number or a number divisible by 2 is obtained? Oh my God, who's making these questions? All right, if a cube is tossed once, this is a dice. Why would they say cube? What is the probability that it is a prime number? So how many prime numbers are there between 1 through 6? So between 1 through 6, these are the prime numbers: 2, 3, and 5. Remember, 1 is not a prime number, and I'm not going to go into why over here. So, and or is divisible by 2 is obtained. So let's take a look. What is divisible by 2? So 2 is divisible by 2, 4 is divisible by 2, 6 is divisible by 2. Now, we don't want to count twice, so we're going to leave this out, right? So that's 1, 2, 3, 4, 5. 5 outcomes total out of 6 possible outcomes. So it's going to be 5 out of 6. All right, number 22. At a school fair, the spinner represented in the accompanying diagram is spun twice. Again, what I would do, maybe try to solve the problems. See, oh, can I do these? If I can, I don't need to listen to this guy yap on about it because I could do this much faster. At a school fair, the spinner represented in a company diagram is spun twice. What is the probability that it will land in section G the first time and section B the first time? So the probability of landing in section G, probability of landing G is going to be 1 out of 4. And then the probability of landing in section B is going to be 1 out of 2. So 1 out of 4 times 1 out of 2 is going to be 1 out of 8. All right. Don't overthink this one. It's not that bad. All right. Let's take a look at another one. Keisha is playing a game using a wheel divided into 8 equal sectors as shown in the diagram below. All right. Each time the spinner lands on orange, she will win a prize. If Keisha spins this wheel twice, what is the probability that she will win on both spins? So the probability of just winning is the probability of going into, let's change this into orange. All right. Just getting this slice here. So that's going to be 1 out of 8. So she's rolling twice, and she wants to win twice. So it's going to be 1 out of 8. First time to roll. Second time to win is 1 out of 8. Remember, the words such as without replacement are not here. So this, we don't have to reduce the probability here. Maybe 1 out of 64. Let's take a look at this. A hard example. Brianna is using 2 spinners below to play her new board game. She spins the arrow on each spinner once. Brianna uses the first spinner to determine how many spaces to move. She uses the second spinner to determine whether her move from the first spinner will be forward or backward. So she spins it one time in one direction, and then she uses the second spinner to see, oh, am I going to move front or back? All right. Find the probability that Brianna will move fewer than 4 spaces and backward. So she wants fewer than 4 spaces. All right, so just what is fewer than 4 spaces? These are fewer than 4 spaces. That's 3/4 of the pie. So that's 3 out of 4. Times, and what's the chance she'll go backwards? And that's half the pie right here. 1 out of 2, that's going to be 3 out of 8, and that's it. Phew. All right. Let's take a look at a couple of these examples. Write the addition rule. Dealing with unions and so on and so forth, and intersections. The addition rule states that the probability of A or B is the same thing as writing the probability of A plus the probability of B minus the probability of A and B. All right, so let's break these examples down so that kind of makes sense instead of just dealing with symbols all the time. In a group of 40 people, 20 have brown hair, 22 have blue eyes, and 15 have both brown hair and blue eyes. What is the probability that neither people have brown hair nor blue eyes? So we have to find, okay, and they don't have anything. So 20 have brown hair, 22 have blue eyes, and we don't want to count twice, so we're subtracting the intersection, and that's going to give me 27. So it's asking which has neither. So there's 40 people, and 27 of them have blue or. So we're going to subtract, and that's going to give me this one right here. All right, let's take a look at the example right here. In a survey of people who bought a laptop, 45% said they were looking for a large screen, 31% said they were looking for a fast processor, and 58% said they wanted a large screen or a fast processor. If a survey respondent selected at random, what is the probability that the respondent wanted both a large screen and a fast processor? So again, let's break this down. So probability of large screen equals 45%. Probability of fast processor is 31%. And 58 said they wanted either or. So let's use the addition rule to solve this. So probability of large or fast is 58%. Now they want us to find the intersection. They want us to find probability of large and fast. This probability of large or fast. All right, so using the addition rule, we can break this down. We're going to use this thing up here. Don't really have a lot of space here, so I'm going to work this number 2 down here. Okay, so again, probability of the union equals probability of each, P of L, the large screen, plus the probability of fast screen, minus the intersection, so P of their intersection, L intersection F. All right. So I'll just probably 58% equals, let's not use percent because that's for probability and not percent. So 0.58 equals large 0.45 plus 0.31 minus, I don't know what this is. This is X because I don't know it. So 0.58 equals 0.76 minus X. If you solve for X, you're going to add X equals 0.18, which is 18%. Okay. Let's do number 3. The probability of math homework is 1 out of 3. The probability of having math English homework is 1 out of 7. I feel like it's the other way around in this school. And the probability of having math homework or English homework is 9 out of 21. Again, this is the or, right? What is the probability of having math and, right? So this is asking for the intersection. So we have a lot of this stuff. So I'm going to break this problem down. So the probability of having math, P of M, equals 1 out of 3. And then the probability of having English, P of E, equals 1 out of 7. And the probability of having or, so I could have math homework one day or English homework, probability of their union, math union, is going to be 9 out of 21. All right, now we just set up the equation like last time. So we're going to say 9 out of 21 equals 1 out of 3 plus 1 out of 7 minus the intersection, which we don't know, so it's x. So if you solve this, you're going to get x equals this number right here, 1 out of 21. X equals 1 out of 21, and that's the right answer. All right. 4. At Andrew Jackson High School, students were allowed to enroll in AP US History if they had taken AP World History or European History. Keywords or right here. Out of 825 incoming seniors, 165 took AP World History, 66 took AP European History, and 33 took both. Given this information, determine the probability that a randomly selected incoming senior is allowed to enroll in AP US History. All right, so a couple of things here. We're going to write the total things we're going to count out of here. Let me work in blue. N equals 825. All right. Probability of world history equals 165 over 825. Probability of European history is going to be 66 over 825. And the probability of both of them is probability of W intersection. Both. Both is intersection. That's this symbol. Is going to be 33 over 825. Okay. All right. So given this information, determine the probability the student is allowed to enroll in AP US History. So this is basically asking, any student who's taken either course can go to AP US History. So this one's a little different. What we're missing here is, what we're looking for here is their union. We're looking for P of W or E, right? And we don't have that. So let's set up our equation. P of W or E equals P of W plus P of E, which is European history, minus their intersection, which is, people taking both, because we don't want to count the same people twice. So this is X right here. We don't know what this is. This is going to be 165 over 825 plus 66 over 825 minus 33 over 825. That's going to give you a number, and 165 plus 66 is going to be 231. 231 minus 33 is going to be 208. So it's going to be 208 over 825. All right, that's the answer. All right. And if you want, you can enroll it, make it a percentage or a decimal. All right. Let's do a couple of more examples here. All right. A suburban high school has a population of 1,376 students. The number of students who participate in sports is 649. The number of students who participate in music is 433. Is the probability of the student participants either is 974 over 1,376. What's the probability the student is enrolled in both sports and music? Again, similar examples. Take a break. Maybe solve the examples first, and then look at the explanation or the answer, and whichever you got wrong, scroll back and be like, oh, I need an explanation for this one. You don't have to watch the whole video, just watch the parts you need. All right, so I want to know the intersection. I know their union. So this is also going to break down into 974 equals 649 plus 433 minus, they're both, right? So 974 is, they take either. 649 definitely in sports, 433 definitely in music. And now I'm trying to find people who were enrolled in both. So let's break this down. Use a calculator here. Use your TI-84 online or so on and so forth. I'm going to type this in. 649 plus 433. That's 1080. So this becomes 974 equals 1080 minus x. So let's just solve for x. 974. So I'm gonna get 108 out of 1376 students were in both. All right, let's take a look at the next example. The probability that a randomly selected teenager uses social media websites F and I are shown below. All right. Given this information, what is P of F and I? Again, we're just using that addition rule over and over here. So we want to know the intersection. So we're going to do 0.77, which is both, equals 0.71 plus 0.52 minus their intersection, which is x. All right, so if you rearrange everything, you get x equals 0.71 plus 0.52 minus 0.77. So put that in, see what you get. I'm going to put it in, see what I get. 0.71 plus 0.52 minus 0.77. Okay, and that's going to be 0.46, so which is this answer right here. All right, what are these colors, man? Let's choose brown. All right, let's do number 8. At Lakeside Resort, the probability that a guest room has a view of the lake is 0.24 or 24%. The probability that a guest room has a queen size bed is 0.74. All right, I'm just going to annotate here. P of lake equals 0.24, and P of queen size bed equals 0.74. Let A be the events of the view of the lake. So I should have kept reading that question. And let B be the event that is a queen size room. So this is P of A, this is P of B. Events A and B are independent of each other. You're given the independence formulas in the regents. All right. And determine the exact probability that a random selected guest has a view of a lake and the queen size bed. So because we're dealing with independence, we can say their intersection, P of A intersection B, equals P of A times P of B. All right. So that's pretty simple. That's going to be 0.24 times 0.76. That's what the first question is asking. All right, so let's plug that in. 0.24 times 0.74. That's going to be 0.1776, you know, the start of the country and stuff. And then let's see the next one. Determine the exact probability that a random selected guest has the view of a lake or a queen size bed. Now, for this one, we have to use the addition rules because, you know, it's looking for an or right here. So we don't know how many can have both, right? So we're looking for the probability of A union B. All right, and that's going to be the probability of A, which is having a lake, 0.24, plus having a queen bedroom, which is 0.74, minus their intersection, which we just found, right? If you have the lake or the queen size bed, was 0.1776. And that's going to be, let's plug that in, 0.24 plus 0.74 minus 0.1776. And that's going to be 0.8024. All right, and that's your answer for this part right here. Whew. Given events A and B such that P of A equals 0.6, P of B equals 0.5, and P of A union B is 0.8, determine whether or not A or B are independent or dependent. All right, so this example, you don't really need to know for the new regents, but I think it just kind of works on, it's helpful to just kind of understand the concept. So if you want, just skip this question, but let's do it together. All right, so P of, we gotta now determine their intersection. So this is asking us to determine their intersection first. So P of A union B equals P of A plus P of B minus their intersection, which is P of A intersection P. All right, so first thing we're going to do is 0.8 equals 0.6 plus 0.5 minus x, and we're going to get x equals 0.3. All right. Well, now that out of the way, now let's determine if they're independent or dependent. All right, let's do that. So we know the intersection. This is one of the independence formula. Intersection equals P of A times P of B. So let's see if that's true. So the intersection we just found was 0.3. So does 0.3 equal 0.5 times 0.6? And yes, it does. So they are independent, because the probability of both happening, either or happening when you multiply them is the chance of both of them happening. They're independent. They're not working with each other for success. Let's take a look at the next example. A student is chosen at random for a student body at a given high school. The probability that the student selects math as their favorite subject is 1 out of 4. The probability that the student chosen is a junior is 116 over 459. If the probability the student selected is a junior, or the student chooses math as a favorite subject, is 47 out of 108, what is the exact probability that the random selected is a junior whose favorite subject is math? Oh my God. Are the event students a junior student's favorite subject is math independent of each other? Explain your answer. That's really terrible. We don't need to know either of these, right? So let's just skip these, all right? Maybe I'll come back at the end of the video and solve these just in a due time, but you don't need to know these for the new regents. But they are done similarly as the previous example here. Okay, now let's take a look at conditional probability and compound events we kind of just did, but they kind of go together. All right, this is the stuff with the given. All right. A public opinion survey explored the relationship between agent support for increasing the minimum wage. The results are summarized in the two-way table below. Find the probability that a participant selected at a random supports an increase in the minimum wage, given that the participant is between 21 and 40 years old. All right, so for these compound events, using these tables. This is something we have to know. It's basically you look at the given thing, right? What is the given thing? So the probability of something given something else. So this is what you're counting out of. This is what you're counting out of. This is your total number of outcomes. All right. So that's key. Make sure you understand what it's asking. Usually, it will actually have the word given, which is great for us. So, given that a participant is between 21 and 40 years old. So, how many people are between 20 and 40? Well, regardless, it's 50, right? So, this is going to be 50 right here. And find the probability that a randomly selected person wants an increase in minimum wage, right? So, how many out of all these 21 and 40-year-olds, how many of these are for increasing the minimum wage? Well, that's 25 of them, right? So we could say this would be 25 over 50, which is 1/2, right? Or 0.5. So again, we're looking for the given, and we're kind of counting out of that given. That becomes our total new number of outcomes. We're not looking at the whole event anymore. All right. All right. Skip these. We did them earlier. So, and then let's keep working. All right. Probability of 200 students are shown in the table below. For this group of students, do the data suggest that the gender and preferred music styles are independent of each other? Justify your answer. All right. First thing you should do when you see problems like this, you should look at the end. Sorry, give me a moment. Just get some water here. All right, sorry, just had to get some water. All right, so first thing you should do is you should count up all the ends of the columns and rows. So 54 plus 25 plus 27. So that's going to be 54 plus 52. So that's going to be 108, 102 here. 54 plus 36 is going to be 90. 25 plus 40, 65. 27 plus 18 is going to be 43. 36 plus 40 is going to be 76. Plus 18, which is going to be 94. All right. And 102 plus 94. And I cannot do basic math, yo. 102 plus 94 should be 196. All right. All right. For this group of students, data suggests the preferred music styles are independent of each other. All right. All right. What's the probability? So then, so what's the probability of let's just check. What's the probability of female? Right? What's the probability of female? I'm just gonna double count. I don't know if I'm actually counting right here. So yeah, you should use a calculator to double check your work. Okay, yeah. So that's where I'm going wrong. This is supposed to be 106. 106. All right. And so that means the total here is 200. All right. So, all right. Now that we have that, again, make sure you add them up all correctly. So the probability of someone being female let's check, right? Does gender and preferred music styles, are they independent of each other? So let's just try female. So probably a female is going to be 106 over 200. All right. Now, let's take a look, right? Preferred music style. Now we found female. Let's say we want to know out of how many technos, how many people like techno, how many of them are female. So probability of female liking techno. What is that going to be? So that's going to be 54 over 90, right? So, and then we're going to check what's the probability of being female. Remember, we're checking this against the probability of being female. The probability of female liking rap music here. Let me do this in a different color. Rap music here. So that's going to be 25 over 65. And then the probability of being female and liking country music right here. So that's going to be 27 out of 45. All right. So let's take a look at these. The probability of being female is basically a little over 50% over here. So 106 over 200. We can clearly see from all these examples here, if you take their decimal amounts, that these, right, being female and liking something is not going to be the same as being female. So they're not independent of each other. If we look at the independence formulas over here, right? Probability of being something given something else is the probability of that thing again. Now, this is 0.54. All right? This is 0.6. So off the bat, we know they're not independent of each other. Being a certain gender, being liking a certain type of music in this example, these things are not independent of each other. And the work they want to show is, and then you could have done it the same way. You could have chosen males and then found out of all the people who like techno, which are males, right? So we just chose female for that one. This is a very, I believe this is actually a really complicated problem here, because it's not using the words given or anything else. And it's asking you to kind of just understand that we have to check female liking a certain music is different from just being female to begin with in the example. So I think it's a very hard example. Ask me about it in class if you have more questions. All right, let's take a look at number 18. A public radio station held a fundraiser. The table below summarizes the donor category and the method of donation. To the nearest thousandth, what is the probability that a randomly selected donor was categorized as a supporter, given that a donation was made online? Again, first thing you should do, you should count up the totals here. This is going to be 1076. This is going to be 2216. All right, and this is going to be 1600. And it's going to be, let me check this, 672 plus 2016. Calculator. $672 plus 2016. So that's going to be 2688. 688. And if you add this up, 2688 to the 1600, you're going to get 4288. So that's your total end. That's what you're counting out of. All right. Okay. So let's take a look. What is this asking? To the nearest thousand, find the probability that a randomly selected donor was categorized as a supporter given that the donation was made online. All right, so we got to look at that given part here. All right, so that's what we're counting out of, the first part. Given the donation was made online, how many online supporters out there? There's 2216. That's what we're counting out of. Given the donation was made online, and how many of those was categorized as a how many of those were so how many of those were supporters, right? So there's 216 patrons and there 1200 out of the supporter class. So this would be 1200 over the total amount of online donations. We're looking at online donations. Out of all the online donations, we're looking at how many of them were classified as supporters, right, in their donor category. And that's going to give us 0.373. All right. Now it's asking, does this suggest that being a supporter is independent of donating online? Now it's asking you to check, what's the probability of being a supporter? Right, that's 1600, right? So, and out of how many people are we counting out of? That's our total, 4288. So that's also going to give you 373. And because these equal each other, then yeah, they're independent. Independent, right? Independent. Not Democrat or Republican, they're independent. The events are independent of each other. That's what they're asking here. This one's a little easier than the previous example because it has that given part. And again, it wants you to utilize these formulas right here, right, in your Regent sheet, right? We've been trying to utilize these formulas right here. All these formulas. That's what we're trying to utilize. The one we utilized was this one in the previous example. Just got to know when to use the formula at what time. All right. Let's take a look. This number 19, this was given as a 6-point problem, I believe, in a Regents a long time ago. So very worth a lot. 6 is the highest for any problem. It's usually the last problem. So let's take a look. Researcher wants to determine if nuts and allergies are related to each other. Researcher surveyed 1,500 people online and asked them if they are allergic to nuts or milk. The survey results are summarized in the table below. Determine the probability that a randomly selected survey respondent is allergic to milk, and determine the probability that a randomly selected respondent is allergic to milk, given that the person is allergic to nuts. Based on the survey data, determine whether or not nuts and allergies are independent events. Justify your answer. So again, give this one a try. It's very, very similar to the previous example. So maybe pause and try to solve it yourself. All right. First thing I want to do, I want to count this up. This is going to be 45. All right. And this is going to be 1455. So this is going to be 1,500 in total. It's going to be 15 plus 1485. All right. Okay, so how many people are allergic to milk, right? How many people are allergic to milk? So 45 people are allergic to milk. So probability of allergic to milk is going to be 45 over 1,500. It's going to be like 0.03, something like that, or 3%. All right. And now it's asking you to determine the probability that a randomly selected survey is allergic to milk, given that the person is allergic to nuts. So given that they're allergic to nuts. All right, so how many people are allergic to nuts? 15. So it's saying probability of allergic to milk given that they're allergic to nuts. So we're counting out of 15 total people. That's how many are allergic to nuts. And out of those, given that you're already allergic to nuts, right? How many of you are allergic to milk? So 3. And that's going to be 0.2. Now saying, are these events independent of each other? Well, no. 3% is going to be 20%. 3% and 20%, they're not equal to each other. They're not independent, like in number 18 right here, right? So no, they're not independent. They're not independent. And we justified our work here, right? Again, this problem is worth a lot because, well, these problems, rather, the last couple, they're very knowledge heavy. They're really asking you to derive a lot of knowledge to answer the questions. Okay, let's do a couple more. Again, try them yourself, see if you get the right answer, and then if you don't, come back to it. All right. Survey a student about our Central High School about television viewing preferences are shown below. Are the event student is a male and student prefers reality TV series or reality series independent of each other? Justify your answer. All right. So let's break this down. First thing, oh, this is great. They already did the rows for us. We don't have to even do that. A student is male, so how many students are male? 230 out of 490. All right. And students prefer reality TV series. So that's going to be reality TV series, I'll write in blue. 180 over 490. All right, 180 over 490. So like they're clearly not equal to each other, right? Like I don't know. This question is kind of obvious. They're clearly not equal to each other. So I don't know what to say. This is a really easy question, right? They're clearly not equal to each other. Well, what they're probably asking is, out of people who like reality TV, how many people are male, right? So first we're going to find P of M, right, equals 230 over 490, all right? And now we're going to find P of M given you like a reality TV series. That's what they're really trying to ask here. So how many of these reality TV series lovers, which is 180, how many of them are male? 70 of them male, right? Now let's calculate the probability here. So I got 0.38. Does that equal 230 over 490, which is 0.47? Well, no, they don't. So they're not independent. No, they're not. Okay? So that's how you do that kind of question. All right. 13. Juan and Felipe are driving at a practice. Juan and Felipe are driving at practice at the driving range before playing golf. I've never played golf before. I don't know if this is what people do. The number of wins and corresponding practice times for each player are shown in the table below. Given the practice time was long. All right, key word here. Given practice time was long, determine the exact probability Felipe wins the next match. First thing we do, all right, add up the totals. 23, 10 plus 12 is 22, 18, 33. Total we're going to get is 45. All right, all the events add up to 45. All right, given the practice time was long, so we're counting out of this part right here. time was long. That's what we're counting out of. Given the practice time was long, determine the probability Felipe wins the next match. So Felipe wins given it's long. So Felipe wins is 12 out of 33. Long practice time. All right. Oh my God, it's not 33, it's 27. Sorry about that. Oh, I'm looking at it, it's like, whoa. This is 27. Got ahead of myself. All right. Well, that's going to be 12 over 27. All right. Determine whether or not Felipe wins and long practice times are independent. Well, let's take a look. Since Felipe winning, let me do blue. Probability of Felipe winning. So probability of Felipe winning is going to be 22 out of 45. All right. Now, again, this is, they're asking you to look at the formula. You could do a lot of work here. All right. I'm going to go back to the formulas. Which formula is it asking you to look at? It's asking you to look at this formula right here. P of A given B is equal to P of A. So remember, in our example, Felipe winning given a long time is 12 over 27. And Felipe winning normally is 22 over 45. Now these two events, right, if you put in the calculator, they're not equal to each other. That's what it's asking you guys to do. That's what it's asking you guys, the girls, to do. Looking at this formula, probability of A given B is the same as probability of A happening. Since that is not true, they are not independent. You're right. No, they're not independent. And your work, justifies the answer. You're right. P of F given L does not equal P of F. That's the formula. That's literally the formula they give. They want you to check that, see if it's true. And clearly it's not. So they're not independent of each other. All right. Number 14. The relative frequency shows the proportion of a population who have a given eye color and the proportion of the same population who wear glasses. Given the data, the events of having blue eyes and wearing glasses independent. Justify your answer. Again, first thing you should do is just tally up the totals here. Annoying, but it is what it is. So this is going to be 0.35. Maybe I should make these a little. All right, this is better. 0.35. Let's see how many people don't wear glasses. 0.20. That's going to be 0.5. 0.65. It's going to be 1. Oh man, it's a lot of adding here. 0.4. 0.35. So this has to be 0.25. All right. Okay. Having blue eyes and wearing glasses independent. So what is the probability of having blue eyes? Okay. What's the probability of having blue eyes? Probability of blue eyes. Probability of blue eyes. It looks like a theta. Probability of blue eyes is 0.4. Yeah, we have that right here. And wearing glasses, is that independent? So now, again, same thing. It's asking you to check this formula right here. Is P of A given B equal to P of A? So now it's asking P of B given wearing glasses, right? Are these two things equal to each other? If they are, they're independent. All right, so what is the chance you wear glasses? What's the chance you wear glasses? out of all the people who wear glasses. All right, so that's blue eyes, 0.4. Out of all the people who wear glasses, 0.35. All right. Now, if you put this in the calculator, this is 0.4. So they're equal to each other. So that means they're independent. Yeah, they're independent. Yes. Our work justifies our answer. Number 15. The transportation methods used by upperclassmen at Calhoun High School are summarized in the table below. Are the events being a junior and driving to school independent? Using statistical evidence, justify your answer. Again, we tally up the totals here. 58 plus 81, 139, 75 plus 39, 114, and then 24 here. All right, and then 58 plus 75 plus 12, 148, and then 81 plus 39 plus 12 should be 132. Yep. 148, and there should be 280 in total, I think. Right? Just gonna double check. There's 280, 139 plus 114 plus 24. No. Okay, see, this is why using your calculator is important. All right. It's gonna be 277. That's 16. It's not 148. 58 plus 75 is 145. Okay, so that's why I was getting something wrong. All right. Are the events being a junior and driving again, they're asking you to check if P of J equals P of J given driving, not walking. Are these equal? All right, so what's the probability of being a junior? That's 145. 145 over 277. Does that equal probability of being a junior while being a driver? So this is asking, is this true? So 58 people out of the people who drive are juniors of the 139 people. So are these equal to each other? No, they're clearly not. If you put it in the calculator, they're clearly not. Well, it's not clear, but if you put it in the calculator, they're not. So they're not independent. No, they're not independent. All right. The table below shows results of gender and music preference. Based on these data, determine if the events in the table is female and the person refers to classical rock are independent of each other. Justify your answer. All right. All right. Let's table it up. No. Let's add all of these things together. 39 plus 17 plus 42 plus 12. That's going to give me 110 on this side. Then 17 plus 37 plus 36 plus 15 is going to be 105. 49 plus 17, 56, 50, oops, 54, 42 plus 36 should be 78, 12 plus 15, 27, this should be 205. All right. Well, I hope that's it, right? Okay. Based on, all right, if the person is female and the person prefers classical rock are independent of each other, again, what are we checking here? Same thing over and over and over and over again. Let me change colors. Let's get aquamarine in here. All right. Person prefer classical rocks. Independent person is female. Well, how many are female? So this is 215. That's 105 over 215. Does this equal person that's female given they like classical rock? I'll use CR for that. Right? And what is classical rock? Right. How many females like classical rock? 36 out of 78. All right. So let's just calculate these probabilities. If you make them into decimals, they're not equal to each other. These are not equal to each other. P of F is not equal. The chance of being a female is not equal to the chance of being female, given you like classical rock. All right. So that's the probability section. There are a couple of more things, just a little bit over Venn diagrams and some union and intersection stuff. Go over with me in class if you need to. If you have any questions about how to dissect Venn diagrams, we could just do some examples right now. So let me just do that. So just a little bit.